Level 1. Lodestone. The simplest place to begin is with a magnet that humans did not manufacture at all. Lodestone is a naturally magnetized form of magnetite, an iron oxide with the chemical formula Fe3O4. Pieces of magnetite are fairly common, but only some become strongly magnetized enough to behave as lodestones, probably after being exposed to powerful magnetic fields in their environment. A lodestone can attract iron, and can also align itself roughly with Earth's magnetic field when it is allowed to rotate freely. This property eventually contributed to the development of the magnetic compass, long before anyone understood what magnetism actually was. The magnetism comes from the microscopic structure of the material. Inside magnetic substances are regions called magnetic domains. Within each domain, huge numbers of atomic magnetic moments point in approximately the same direction. In an ordinary unmagnetized piece of material, different domains may point in different directions, causing their magnetic effects to mostly cancel. In a permanent magnet, many of these domains become aligned. The result is a magnetic field that extends outside the material, with what we conventionally call a north pole and a south pole. Cutting the magnet in half does not isolate those poles. Instead, each piece becomes a smaller magnet with its own north and south ends. Lodestone is therefore relatively weak compared with modern magnets, but it established the basic phenomenon that every later level takes much further. Level 2. Ferrite magnets. Ferrite magnets are probably some of the magnets you have encountered most often without noticing. They are the familiar dark gray or black ceramic magnets found in speakers, small motors, refrigerator magnets, sensors, and countless inexpensive devices. They are generally manufactured from iron oxide combined with elements such as barium or strontium. Unlike a solid piece of metallic iron, ferrite is a ceramic. The ingredients can be processed into a powder, shaped, and heated until the particles bond together into a rigid magnetic material. During manufacturing, magnetic fields can help orient the microscopic structure so that the finished magnet develops a preferred magnetic direction. Ferrite magnets are not particularly powerful compared with the strongest permanent magnets available today. Their advantage is everything else. They are inexpensive, resist corrosion reasonably well, and can be manufactured in enormous quantities. They also have relatively high electrical resistance, which can reduce unwanted electrical currents when they are used around changing magnetic fields. This makes ferrite useful in electric motors and loudspeakers. Inside a speaker, for example, a permanent ferrite magnet interacts with a coil carrying and changing electric current. The resulting electromagnetic force moves the speaker cone backward and forward, transforming an electrical signal into sound. Ferrite demonstrates an important rule of engineering. The strongest magnet is not automatically the best magnet. Sometimes a cheap magnet that performs reliably for decades is much more useful. Level 3. Alnico magnets. Before rare earth magnets became widely available, some of the strongest practical permanent magnets were made from a family of alloys called alnico. The name comes from three of its major ingredients: aluminium, nickel, and cobalt. Iron makes up much of the remaining material, sometimes with smaller additions of other elements. Alnico magnets can produce strong magnetic fields and, importantly, they retain useful magnetic properties at temperatures that would cause some modern permanent magnets to lose much of their magnetization. This temperature resistance made alnico extremely valuable in devices such as electric motors, measuring instruments, microphones, speakers, and sensors. There is a trade-off, however. Alnico can generate substantial magnetism, but it is comparatively easy to partially demagnetize if it is exposed to an opposing magnetic field in the wrong configuration. Its shape therefore matters, and long alnico magnets generally maintain their magnetization better than short flat ones. The alloy also introduced engineers to a more advanced way of thinking about permanent magnets. A useful magnet is not defined only by how strong its field appears at the surface. Engineers also care about how resistant it is to being demagnetized, how much magnetic energy it can store, how it behaves with temperature, and how expensive it is to manufacture. Those considerations become even more important at the next level. Please consider subscribing if you're enjoying the video so far. I'll be uploading many interesting videos regarding physics, tech, and chemistry. Level 4. Neodymium magnets. Neodymium magnets are the small silver-colored magnets that can feel almost absurdly strong for their size. They belong to the rare earth magnet family and are primarily made from neodymium, iron, and boron, producing a compound commonly represented as Nd2Fe14b. Despite the name, neodymium is not the only thing responsible for their strength. The particular crystal structure formed by neodymium, iron, and boron creates an extremely strong preference for magnetization to point along particular directions inside the crystal. Once many microscopic grains have been aligned and magnetized, they resist having their magnetic orientations changed. This allows neodymium magnets to produce extremely strong magnetic fields relative to their size and mass. A tiny neodymium magnet can therefore replace a much larger ferrite magnet in some applications. They appear in headphones, hard drives, electric motors, generators, magnetic couplings, sensors, and many other compact devices. Modern electric vehicles are one particularly important application. In certain motor designs, powerful permanent magnets interact with magnetic fields generated by coils to produce rotation. Increasing the magnetic strength while keeping the motor compact can improve power density and reduce the amount of space required. But neodymium magnets are not perfect. They can be brittle, they can corrode without protective coatings, and some grades lose magnetic performance as their temperature rises. Their strength can also make surprisingly small magnets hazardous when they snap together or attract nearby metal objects. Once again, greater magnetic strength creates new engineering problems rather than simply solving old ones. Level 5. Samarium cobalt magnets. If neodymium magnets are extremely strong but can struggle in certain hot or harsh environments, samarium cobalt magnets offer a different combination of properties. These are another type of rare earth permanent magnet, primarily containing samarium and cobalt. They are generally not able to match the very highest magnetic energy densities of the strongest neodymium magnets, but they can retain their magnetism much better at elevated temperatures. They are also highly resistant to corrosion. This makes samarium cobalt useful in environments where reliability matters more than obtaining the absolute greatest magnetic strength for the lowest price. Applications can include aerospace systems, specialized motors, sensors, scientific instruments, and equipment operating across large temperature ranges. The downside is cost. Samarium and cobalt are relatively expensive materials, and the magnets themselves are brittle and can be difficult to manufacture. This creates an interesting comparison. Ferrite is relatively weak but cheap. Neodymium is exceptionally powerful and compact. Samarium cobalt sacrifices some of that maximum strength in exchange for greater thermal stability and resistance to harsh environments. There is no single perfect permanent magnet. But at this point, we can stop limiting ourselves to permanent magnets entirely. Level 6. Electromagnets. A permanent magnet creates a magnetic field without needing a continuous external power source. An electromagnet does almost the opposite. Its magnetic field exists because electric current is flowing. When electric charge moves through a wire, it creates a magnetic field around that wire. If the wire is formed into a coil, the magnetic fields produced by many sections of wire reinforce one another. The result resembles the field of a bar magnet with a north-like end and a south-like end. Place a magnetic material, such as iron, inside the coil, and the field can become considerably stronger. The external field encourages magnetic domains inside the iron to align, turning the core into a temporary magnet. The major advantage is control. Increase the electrical current and the magnetic field generally becomes stronger. Reduce the current and it becomes weaker. Reverse the current and the magnetic poles reverse as well. Turn the current off, and much of the magnetism can disappear. This makes electromagnets useful in machines where magnetism has to change dynamically. Electric motors use changing magnetic fields to produce rotation. Relays use electromagnets to move electrical contacts. Industrial lifting magnets can pick up large quantities of ferromagnetic metal and then release them when the current is switched off. But ordinary wires have electrical resistance. Push a large current through them and they heat up. Eventually, heating becomes one of the main limitations on how strong a practical conventional electromagnet can become. To move past that limitation, We need a material that can carry current with almost no electrical resistance. Level 7. Superconducting magnets. A superconducting magnet is an electromagnet whose coils are made from superconducting material. Below a particular critical temperature, a superconductor can carry electrical current with essentially zero ordinary electrical resistance. This allows extremely large currents to circulate without producing the enormous resistive heating that the same current would create in a normal metal wire. The catch is that the magnet must be extremely cold. Many powerful superconducting systems operate only a few Kelvin above absolute zero, and therefore require cryogenic cooling using substances such as liquid helium. The benefit is enormous. Superconducting magnets can generate strong, stable magnetic fields for long periods, making them essential in some of the most advanced machines humans have built. An MRI scanner uses powerful magnetic fields to influence the magnetic behavior of atomic nuclei inside the body. Radio frequency signals disturb those nuclei, and their response can then be used to reconstruct detailed images of internal tissue. Particle accelerators use superconducting magnets for a very different reason. Charged particles moving near the speed of light naturally want to continue in a straight line. Powerful magnets bend their trajectories and keep the beam traveling around the accelerator. Other magnets focus the beam into an extremely narrow region before collisions. Fusion experiments also rely on enormous magnetic fields. Because plasma can reach temperatures where no ordinary solid container could touch it, magnetic fields can be used to influence the paths of its electrically charged particles and help confine the plasma without physical contact. But even superconducting magnets have limits. If the field, current, or temperature becomes too extreme, part of the material can suddenly stop superconducting. This event is called a quench. The stored magnetic energy then has to be managed extremely carefully. Level 8. Pulsed magnets. For the strongest laboratory magnetic fields, engineers sometimes give up on keeping the field running continuously. Instead, they generate an enormous field for only a very short time. These are pulsed magnets. The basic principle is still electromagnetism. An enormous electric current is sent through a specially designed coil, creating an intense magnetic field. But rather than maintaining the current indefinitely, energy is released into the magnet in a short pulse. This helps because many of the problems limiting magnet strength depend on time. A huge current heats the conductor. An enormous magnetic field also produces equally enormous mechanical forces inside the coil. Different sections of the magnet effectively push and pull against one another, placing the structure under extreme stress. If the magnet had to survive those conditions continuously, the required cooling and structural strength would become incredibly difficult. A short pulse allows researchers to briefly reach fields much stronger than many steady-state magnets can maintain. In some experimental designs, the magnetic pulse is so extreme that the magnet itself cannot survive it. These are known as destructive pulsed magnets, because the coil is sacrificed during the measurement. The experiment may last only a tiny fraction of a second. But during that moment, scientists can investigate how materials behave under magnetic fields that are otherwise impossible to create in a laboratory. Strong magnetic fields can alter electrical resistance, change the organization of electrons inside materials, affect superconductivity, and reveal previously hidden quantum behavior. Researchers therefore do not build these magnets simply to attract the largest piece of iron possible. At extremely high field strengths, magnetism becomes a tool for changing and investigating the fundamental state of matter itself.